If we got the right bug at the right time, then yeah, sure, we can have a new compound. Yep.
When Alexander Fleming discovered penicillin here in London in 1928, it changed the face of medicine. Antibiotics like penicillin have saved the lives of millions around the world, and modern healthcare is reliant on their use for surgery, cancer treatments, and to prevent the most simple of infections becoming fatal. But resistance to antibiotics is growing at an alarming rate, with projections that by 2050, drug-resistant infections could kill more than 10 million people a year worldwide. I'm Dr. Geoff Lacey, and in this special episode of The Cure, I'm travelling from the hospitals of London to the caves of South Dakota to the townships of South Africa to explore the terrifying prospect that this era of antibiotics is coming to an end. Antibiotics work by killing or preventing the growth of bacteria. Resistance to antibiotics is a natural phenomenon brought about by genetic mutations. But the enormous use of antibiotics has accelerated this process. As sensitive bacteria are killed, the resistant bacteria are left to thrive and multiply. One of the foremost experts on antibiotic resistance in London is Dr. Vanya Gant at University College London Hospitals.
Antibiotics have been abused and abused and abused to the point where all the bugs have learned that they should become resistant.
Yeah.
And by becoming resistant, it means that we have lost the ability to treat our patients. That's why I'm so worried.
So even in the last few years in your clinical practice, you've seen an escalating problem.
For example, we have on this ward today a lady who's got an organism called Klebsiella, and her Klebsiella is totally antibiotic resistant. And that
Totally
is
resistant?
Totally resistant. It is untreatable. This is here now, today, on my ward.
The UCLH Microbiology Laboratory receives and analyses all the specimens from its hospital sites to select those antibiotics which will work for the patient.
You see this greenish colour?
Yeah.
All the green colour is bacteria and it's growing all over it. If you look more closely, you've got 3 little discs on there, and those discs are loaded with antibiotic. And that one is keeping the bug off.
And then these 2 antibiotics are actually, there's a resistance to those.
Yeah.
So the patient with this infection
Would need
that antibiotic, but if they took any of those,
it would be useless.
Emily Osborne, the patient with resistant Klebsiella, has also had her samples analysed here.
Good morning, Tina. How are you? All right? So we've been talking a lot about our patient up on the ward who has this very, very, very resistant organism. And I gather that's it on a plate, isn't it?
This is Emily's sample plate
exactly right.
itself.
That is her bug. All these antibiotics are useless against that organism. And the bug just learnt. Every time, learnt to be resistant against one more. And this is where we are now.
The resistant bacteria that infects Emily are such a danger to public health that she has to be isolated to minimise the risk of them spreading. As part of the strict infection control policy, we can't take our camera equipment into the room.
We are good to go.
So, Emily, how long have you been here now?
8 weeks.
Wow.
8 weeks.
8 very long weeks.
Were you aware that there were, bugs out there that we had lost power to treat?
No, you automatically think, oh, well, I've got a bacteria, there's antibiotics to treat it.
The good news story is that with your scan today, I'm pretty sure the drain can come out and then you can go home to your baby daughter.
Yeah.
So you've got a baby daughter?
Yeah, I've got a 2.5-year-old.
Oh no. So has she been able to visit at all?
No.
You've not seen her for 8 weeks?
No. I've got pictures, but I've not actually seen her.
Well, thank you very much, Emily, for letting me come and see you and chat. And I'm very pleased you're on the mend.
Yes.
Emily has been lucky enough to have access to some of the most advanced medical facilities and treatments available today. But even this isn't always enough to save patients like her.
Antibiotics are natural molecules made by bugs and fungi. In the war of bug on bug, if you want, we stole all that and we mass produced it and threw it back into the environment, back into the food chain, and we didn't know when to stop.
So have we almost started this battle too late?
Oh, we have, without a doubt, without a doubt. I know that the next 10 years, at the very least, are going to be very, very, very tough.
The World Health Organization has described antibiotic resistance as one of the most serious global health threats of our time and is urging all countries around the world to help combat the threat.
If we look in Europe, for example, we see currently that probably 25 to 30,000 people per year die because of resistance.
At the moment?
At the moment.
Wow.
And this will be expected to increase over time unless we begin to reverse the issue. Doesn't matter whether you're a developed country, doesn't matter whether you're a city, whether you're in a rural area, you find it everywhere. And this is because we live in a time where people get on planes, they travel anywhere. So if you're carrying a resistant bacteria and you're in one part of the world and in 24 hours you're on the other side of the world, you may have brought that over to that part of the world. Antibiotics are misused in a lot of ways. People use them when they don't need them, or if they don't use them in the right way that they're prescribed, that can contribute to the development of resistance. We use a lot of antibiotics in other ways, for example, to raise animals so that they get bigger. In many countries, we don't have good mechanisms for regulating the use. So somebody may just go to a pharmacy or store and get antibiotics and treat themselves. And in a lot of respects, we also don't have good diagnostic tests to say, are we dealing with an infection which can be treated by antibiotics, or are we dealing with a different kind of infection?
This seems such a big problem. What can we do to address the issue?
We have to have actions taken by physicians, by farmers, by regulators, and so this is really the next challenge. What we have to realize is that it's not going to turn around overnight, and this is going to probably be the dominant concern about infectious diseases for the next decade, or perhaps even longer.
The misuse and overuse of antibiotics by people is having a clear impact on the spread of resistance. But the use of antibiotics in farming is also a huge cause for concern, with an estimated 63,000 tons of antibiotics fed to farm animals every year worldwide. Nearly 45% of all antibiotics used in the UK is in farming, an issue that Richard Young has been campaigning about for decades. Hello Richard, I'm Geoff Lacey. Nice to meet you.
Nice to meet you.
How are you?
Okay, enjoying the nice sunshine.
I know, exactly. So what are you up to now?
Well, we've got a cow that calved at the end of last week.
Yeah.
And she's got retained cleansing. And we took a temperature early this morning and it was 104.4.
Wow.
So we want to just check her temperature.
Yeah.
If it's still up in that sort of area. I spoke to the vet and I've got some antibiotics and I'm going to treat her with them.
Do you need a hand?
If you can help me walk her in.
Yeah, no, I'd love to.
Right, just bring the gate round now behind her. So what I'm going to do now is just take a temperature, and it needs a good half minute, but I'll keep my hand on it because sometimes I'll push it out and then I get a broken thermometer.
That would be unpleasant. This is a classic example on your farm as to when you would use antibiotics, i.e. as a reaction to clinical need.
The only time we use antibiotics before they're needed is if we have to do an operation on an animal, like a caesarean.
Yeah.
Where the concerns are with very large farms where there are a lot of animals are kept together. Rather than waiting till they become ill, the tradition has been to put them on low-level antibiotics in their feed or their water for a large part of their lifetime as a preventative method.
Some of the antibiotics used on animals are also used in human medicine, and the overuse of them in farming means that the bacteria in animals can develop resistance to these antibiotics. These resistant bacteria can then be passed on to humans through the consumption of meat and contaminated crops.
No, I won't need my glasses to read this, we'll see. It's only 102.8.
0.8,
And to be quite honest, I'm not sure she does need antibiotics. This is the antibiotic I'll be using.
Yeah.
And it's exactly the same antibiotic that it's used in human medicine.
Yeah.
Until about 10 years ago, it was widely used to treat urinary tract infections, I think, in people. But now there's quite a high level, almost half the cases of urinary tract infections are resistant to this antibiotic.
Most intensive farming relies on antibiotics to prevent disease and increase growth rates among livestock, all to try and meet the enormous global demand for cheap meat.
Is that all you want, sweetheart? That's probably all she wants. The whole food system has become something like a conveyor belt. Intensive chicken producers can make as little as 2 pence a bird profit. If the chickens get an infection, 1 day extra feed will take out the profit. 2 days turns that profit into a loss.
What are the actual solutions? How can we solve this problem?
If consumers understand that actually their cheap chicken isn't as cheap as it seems because they could pay for it in a very expensive way through a resistant infection, not necessarily at that time but later in life, I think that all consumers would be happy to pay that little bit extra to avoid this problem. It isn't just about farming, and it isn't just about human medicine. It's about everything, because we all live in the same environment, and bacteria transfer between countries, between continents. Effectively, we're all part of the problem.
Antibiotics are complex organic compounds that are found in the natural environment. But with no new class of antibiotics discovered for nearly 30 years, scientists are now being forced to travel to some of the most extreme places on the planet. One of which is the Wind Cave of South Dakota in America, one of the longest caves in the world with over 142 miles of passages.
Most of our antibiotics, like streptomycin, came from soil microorganisms, and we've exhausted that supply. So we have to go to new and unique and novel environments. So people are looking all over the world. Deep oceans are one, hot spring pools, deserts.
So all extreme environments,
Right.
because that's where you think the source of new antibiotics
Right.
will lie. So you've very kindly agreed to allow me to join you on the expedition
I know,
today.
yes. and very, very few people have been ever where we're going.
Really?
So, yeah.
The team and I will be underground for 12 hours, aiming to reach a deep underground aquifer where we will collect samples. This is the first time I've ever been caving. Hazel, do you want me to take any of the science stuff? Or
We've got enough to worry about. You got something to pee in?
something to pee in?
Yeah, well, you're not peeing in the cave. You are a walking resource, so if
Thank
you dump all your urine down there, then they don't need to fight anymore. So
See.
yeah, we definitely don't want to leave a trace.
Okay, I'll make sure my pee bottle is packed.
Now, there's a really good foothold stuff.
There are no words. I'm definitely aware that, you know, as we're going in, we're getting more and more remote.
They call that distance anxiety. There's a rescue. We've got to get you out. The only way to contact someone is for these guys to run to the entrance and tell someone there's a problem. It's hard to break your back, but there are some places in some caves, if you break your back, you're going to have to be hospitalized in the cave because you can't be evacuated from it.
My word.
Yeah.
So how far do you reckon till the sample site?
So we're probably 2/3 of the way.
Okay. So it sounds like it's pretty infrequently visited down here then.
You know, more people have, on average, summit Mount Everest every year than have ever in history been down here. So
Really?
people are going to be the biggest impact, so we reduce that to just what we need to do to get things done down here.
In isolated places like these caves, bacteria have to fight in order to survive, which may include developing antibiotics as a means of attacking other bacteria.
The trick is figuring out where to put your foot where you don't fall back in. So I haven't done this bit in a while, Josh, so if I fall in, don't do what I just did.
It gives me great,
Yeah.
great confidence.
Yeah, it's not too bad actually. It's pretty good on this side.
After 4 hours and a descent of 700 feet, we finally reached the lake. This is the lakes, is it?
Yes. Not many people ever get to see an aquifer like that. A couple of 100 feet back in there. It's deep and beautiful. And it looks really dirty, but this is actually calcite. So a lot of the stuff that we're standing on, all this shiny stuff. And so this is actually a cave formation forming on the surface of the water. So it's not dirty, it's uber clean. It's super clean. We talk about starvation, and you know the term we use is oligotrophy, but this is ultra oligotrophy. There's a billion plus years of microbial evolution where there's this arms race, and if we can leverage every aspect of that arms race, then we increase our likelihood of finding something that's more difficult for resistance to develop. But there's no body of water on Earth that has numbers of bacteria as low as this.
Really?
Yeah, so if you want to study them, you have to collect millions and millions and millions of them.
We need to get to work then.
Yeah, come on, we got a lot to do. Oh, please work. That's always the worry when you get down here. There you go. Uh-oh. Well, at least we know there's power in there. It's got the squash, that's it.
That's promising.
Yay.
Making the right noises.
It's a 1 in 10 millionth of a millimeter filter, so it's a big filter, but it's got holes that small. And the bacteria are bigger than that, so the bacteria get trapped.
Hazel takes as many samples as she can during the time we have at the lake. So within one of these many samples today, we could potentially have the key to the next antibiotic.
If we got the right bug at the right time, then yeah, sure, we could have a new compound.
Fab. The samples that Hazel and the team have collected will be taken back to her lab. They will look for genetic clues in the bacteria by extracting DNA to determine whether they contain novel antibiotic compounds. This is followed by the painstaking process of trying to grow these organisms in the lab to make new antibiotics.
You did good. You did really, really good.
Yeah, I feel quite, weird. Yeah. Like you've just come from
the middle of the earth.
Yeah, it's like you just come out. I don't know. I can't even.
And the thing is, you spent all day in it, so like the grass looks kind of different, and you get the smells.
Honestly, guys, thank you very much for taking me down there, and I hope the science rings through and we find something from that trip because it deserves it. In 2013, multi-drug resistant tuberculosis infected an estimated 480,000 people worldwide. One of the big factors contributing to the spread of drug-resistant TB and other antibiotic-resistant diseases is the length of time it takes for people to be diagnosed and to start receiving the correct treatment.
That 3 months period where you're putting somebody onto a regimen where probably they're only getting 2 effective drugs. You're just driving further resistance to the drugs that you already have. You see people dying before they get to hospital and continuing to spread DRTB across the community.
Every patient at the clinic has multi-drug resistant TB and is given a specific regimen of drugs in the hope they can be cured. So Tamtam, these are Onke's TB tablets, is that right?
These are all Onke's tablets.
How long have you been here, Onke, at this unit?
That was my 3rd month. I was working in the farm, then it was raining, so I thought maybe I got it's a cold. Then they gave me antibiotics. I went home when the coughing started getting
worse.
And then I went to the clinic.
You can go and take your treatment.
One patient from the township who initially received the wrong diagnosis with drastic consequences was Pumeza Tisili.
It was in 2010, right? And it was the World Cup.
Oh, yeah.
So I went to the clinic and the private doctor. They didn't see what was wrong with me.
Yeah.
So then they will prescribe a Panadol, you know, Panadol.
Yeah, paracetamol, yeah.
But they didn't work.
After several months of misdiagnosis, Pumeza was eventually put on a course of antibiotics for extensively drug-resistant tuberculosis.
So from there I was given 20 tablets right at that moment and an injection. And then one morning I woke up and everything was quiet. People were talking, I had no idea what they were saying. It was due to the kanamycin injection that I took.
Injection you were getting. So how long were you on treatment for in total then?
3.5 years about.
3.5 years?
And about 30,000 drugs. But I can't really blame the doctors because they couldn't see anything on the so.
Your first infection with TB was XDR, was extensively resistant. So.
And I didn't know anyone who had TB at the time, but I've catch it anyway because it's in there.
Because it's just got out there and in the community, and you've got cochlear implants.
It's amazing.
Is it?
At least now I can listen to music.
Wow.
It's not really groovy yet, but I catch it.
I assume you're very lucky to recover from XDR because it can be fatal.
There were like 10 of us who were studied on the drug, linezolid. Not all of us made it. 2013, right, I wrote the drug-resistant TB manifesto, and then last year I delivered it at the World Health Organization. Well, the demands, they are simple. We need better drugs, better things to test the
Better
TB.
diagnostics, So you need action now. Developing diagnostic tools that are quick, accurate, and can be used in the field are vital to get people on the correct antibiotics quickly and thus reduce the spread of resistance. One of the most exciting tools being developed is the QPOC. I assume this is the QPOC thing.
It is essentially what you can see behind us shrunk down into something that's portable, battery operated, and we can take into the field. So right now this one is focusing on drug-resistant TB.
So take me through what would be the process.
So we get the sputum pop, and then we have to add a special thinning liquid, obviously to release the mycobacteria from the sputum. And then, quite simply, we interface that with the cassette so that the mycobacteria goes into the cassette. We put it into the device, and we press go. And it's as simple as that. 15, 20 minutes later, we'll have a result.
The QPOC not only tells you what infection you have, but also tells you which antibiotic it is resistant to.
So this patient's coming up as positive for TB, and then also positive for 2 drug resistance.
Clinical trials for the QPOC are expected to start in mid-2016, with the device being launched by the end of that year.
It's the DNA that we're really interested in this instance. And so we've created a special filter that when you push it through the filter, then pure DNA comes out the other end. And this happens in minutes. And then the next aspect is to read them. And we find certain mutations that have been clinically characterized to produce drug resistance.
Right.
And so we then target them.
And just to confirm again, I wouldn't need any other piece of kit apart from this handheld device to do all that.
That's it. We're really interested in antimicrobial resistance, not just for tuberculosis, but for things like gonorrhea and chlamydia, HIV, etc.
So you tell me that you potentially could develop the QPOC to analysing all the major pathogens that affect humans?
Absolutely.
I'm almost speechless. No, just because, you know, as a clinician, I'm aware of the limitations that face you in terms of treating infectious disease and some of the lengths involved in making sure you have the right antibiotics for that patient, and often initiating them on what then turn out to be the wrong antibiotics and the impact that has on resistance and that patient's care. Whilst this just negates all that.
We're certainly hoping that this will change the game.
Phenomenal. In this journey across the world, it's become absolutely apparent how significant the growing resistance to antibiotics is to global health. It's also been heartening to see the number of experts going to huge lengths to try and steward the use of antibiotics, prevent their misuse, and pursue the challenge of drug discovery.